with that nice picture, it's that picture at the end where we have those two sorted bits here, right? Where we have one sorted thing here and another sorted thing here. And then we combined all of them into a single sorted thing with both pieces. So let's take another look at, like, especially that last picture. Now, it's hard to see with the number of elements, but we're not doing this process just at the end. All of the little bits get sorted the same way. We're building our left side and our right side. Each of those pieces are sorted. Then we merge those two sorted arrays together. Then, once we have our last two, we merge those together, and then we have our final sorted array with both of the elements, or all the elements from both arrays inside of it. So, how does this actually work? What is it doing? Yeah?
It's not actually going through the entire array all at once. It's still starting from the back until it gets to half, and then it splits off and does it again.
Exactly. So, the comment is that we're not going through everything. We're only looking at like half of it at a time, kind of, right? And within those, like maybe we're only looking at a quarter of it at a time or something, right? As you look at how the pieces are moving around. That's exactly right. And that's what you should be looking at for that. We're dividing by two a lot structure. So if you focus on which pieces we're looking at, we're building these complete parts that are like smaller sorted versions of the whole array. Right, so we kind of build this one section here that's sorted like on the left, and then we give up on it. And we build this other thing on the right, and then we smash them together. We'll do the same thing on the right side. We're going to build two different arrays, a sorted bit on the left, and then a sorted bit on the right, and then we smash them together. Now we have a sorted bit on the left, a sorted bit on the right, and now it's so like the other algorithm, they were proof about because we're doing a lot of the divide and conquer type stuff. The same process, but repeated over and over again. And then we end up with our sorted array here. So, that's what it is visually. At a glance, what we have as part of the process here is the following. So we have our array here with a bunch of elements in it. I don't know why I keep dealing with this. And so with each of these elements we have in our picture, our first step is we just straight up cut the left side and the right side. Quicksort went through this whole process about trying to figure out what a good pivot is, making the smaller things on the left, the bigger things on the right. mergeSort keeps it simple. mergeSort just says, split it. We'll deal with the left side, then we'll deal with the right side. We'll figure out later how to actually make them be part of a single array. Then it takes this left side and says the same thing. It says, split it. Two pieces. It takes each of these here, and it says, split it again. All right, well, we split a bunch, now we only have one element in every array, right? Once we have one element in every array, we can say, okay, well, these two are together. These two here. If we have these two things together, we can then smash them together and just look at which one's sorted. Okay, well, this one's smaller, so we want this one to be first. And then this one's bigger here. We'll do the same thing on this side. This is smaller, this is bigger. Now the clever part comes in. We want to take these two arrays. We know both of these are sorted because we just had a single element, and you and I know if we just have two elements in constant time, we can just build a new array where the smaller one is the first one, and the bigger one is the second one. So that's constant time. That's easy. Now comes a trickier bit. We know that both of these arrays are sorted. We're guaranteed for that because we know that this step, just put the smaller one first and the bigger one second. Given that these two arrays are both sorted, we need an algorithm that can combine these sorted arrays into a single sorted array and do it in linear time. Why linear time? Because as we go through the mergeSort process, we'll end up cutting a bunch of times to the side here. Right? We'll be splitting in half every time until we end up with a bunch of single elements. If our merging of the pieces together was slower than linear time, then that would make our whole runtime worse. We can see that we're going to end up with the same structure that we saw for quicksort with one additional step. We'll take our original array here. This splits into these two smaller arrays. Each of these splits into smaller arrays, and eventually they split off into individual pieces. So this structure that we see here is our go-to, we're doing some type of logarithmic algorithm, has a log in it somewhere. We know the depth of this is going to be log base 2 of n, log of n. Right, because we started off with 1,000 elements, and then we had 500 and 500, and we keep cutting until we got down to single elements. So the depth of this is log base 2 of n. Once we end up with all of these elements here, we need a way to put them back together. We haven't done any work yet, really, to iterate over this here. Guess we had to copy them into a new array, maybe, but this is pretty free. We need to make sure that while we're traversing these on this line here, we need this runtime to be linear. If we had a quadratic algorithm for combining this stuff, like let's say we had a sorted left side and a sorted right side, and we used insertion sort to make a new array, this would be quadratic, and this whole runtime would be worse than quadratic. So that's no good. So we need to make sure that we have an algorithm that can take two sorted arrays, smash them together into a single sorted array, and do that by only looking at every element once. So that algorithm is, I've seen people get on interviews before to just do that part of it, so that's a good one to go. Spend some time going over it. But that's the merging part of mergeSort. So the algorithm that can combine, so once we merge these here, and we take and merge these here, merge these here, merge these here, the algorithm that can take these two things as sorted arrays and smash them together into another sorted array is the merging of it. So while we go and code this here, we're going to split into two pieces. We're going to first build the merging part, where we say, if you happen to give me two arrays that are both sorted, I'm going to write a function that gives you a third array that's all of the elements that are also sorted. Then we're going to use that algorithm to say, after we cut this up into individual pieces and only end up with these single bits, let's go ahead and merge the left and the right pieces together up until we only have our one array with all of the stuff in it. So let's take a look at that merging algorithm first, and then we'll come and revisit what those pieces look like together. So opening up a playground here. Get started with a playground. Call this mergeSort. Okay. All right, put this in presentation mode. Okay, so the first algorithm we're going to want to build, and we'll see how all the pieces fit together, is that merging part. We'll treat this as a separate like DSA whiteboarding question, and I'll try to model some of what I'd want to do in that process. We want to write a function called merge that takes in two sorted arrays of type, might as well be nice and genericize it, some type T. We take in two sorted arrays, sorted R2, and we take in some way to know whether or not the order of them is correct, some isSorted closure. By isSorted. So this will tell us how these arrays are sorted. And this whole function is going to give us another array, which is both of them together. So we have our function. We might not be sure what it does yet, but we know that what its signature is supposed to be. We're getting in two sorted arrays. We're going to merge sorted R1, sorted R2, and we're going to use this closure is sorted to dictate what does it mean for these things to be sorted. With that, here's how our process is going to work. So we need some algorithm that's going to do it in linear time here. So what do we have? We have two arrays. Let's say we have 3, 6, 7, 10. We have another array which maybe is 4, 5, 8, 11, 12. Could be the same size, don't have to be the same size. And we want to build another array from both of these that has the elements 3, 4, 5, 6, 7, 8, 10, 11. Is that right? 3, 4, 5, 6, 7, 8, 10, 11. Good. So these are the inputs to our function. So this would be R1, this would be R2, and then this we want to be the output. Question? Yep. Yeah. We will need to give this something sorted, right? The clever part about mergeSort is mergeSort's first step is dividing in half until we get to arrays with a single element in them. They have to be. We only have one element in them, right? So it's a function you have to be careful with, because you're exactly right. If this array had like 15 at the beginning, this whole house of cards would fall apart. We need these things to be sorted. But mergeSort, very cleverly, breaks it up into these single arrays. And if an array only has one element in it, it's sorted. No way for it not to be sorted, right? So we'll take advantage of that structure and this algorithm combined to build that whole method. So let's take a look at what we want with this function here. Now, how do we go from these inputs to this output? And how can we do it in linear time? So the restriction on a linear time algorithm is we have to look at every element only once, or only a constant number of times, right? We're not allowed to just like take these and say, well, add the arrays together and then do bubble sort. Why would we not be able to do that? If we're trying to find a linear time algorithm. How long does bubble sort take? Forever is a good answer. In terms of big O, do you remember? M squared, right? So it's a quadratic algorithm, we have two nested for loops, right? So the thing we have to avoid in what we're coding here is nested loops that are going to look at everything. We need to find a way to make sure that we're only looking at every element a constant number of times, basically once. Say more, what do you mean?
So we're going to be at index 0.
Mm-hmm.
And we're comparing it to index 0 in the second array.
That seems like a good place to start.
If the left side is smaller than that side, then it'll append it to the new array.
Okay, I like where we're starting.
If it's not, then it's going to check if the second array is index 0 or greater, and then it'll append that.
Okay.
And then it you increase the index for that specific.
Good, I like it. So talk me through this. Let's give a name for this index here.
So like
This is maybe R1 index,
R1
and maybe we'll call this here. It's a good name. 2 index. Okay. So you're talking us through our algorithm. So R1 index starts at 0. R2 index starts at 0. All right. What do we do now?
The condition we're checking is that R index, R1 index, that value is greater than
Yeah.
R index 2.
Yeah.
R2.
Yep. That's right.
I'm not saying
No, you are. We're checking to see if the value at R1 index is less than the value at R2 index.
So in this case, the left's the R1 index,
Mhm.
the value of that is less than.
Yep.
So that's the first thing we're going to put in the array.
Good.
And then we increase that index's value by 1. So now our R1 index is going to be index 1. So now we check if that index is less than R2 index 0.
Yeah, the value at R1 index is less than the value at R2
So
index.
it's not, so
Yeah.
in this case, then we increase, no, we have another condition that checks, right?
Mhm.
If R2 index is less than
If the value at R2 index is less than the value at R1 index.
And then, so in this case, it's true, so then we append our two indexes current place into the array, and then we increase that value by 1.
Exactly. Then we'll keep going, right? We'll compare the 5 and the 6. We see that the 5 is less than the 6 here. So the 5 goes in, and this index jumps up here. We compare the 6 to the 8. The 6 is smaller. That goes in. This index changes. We compare the 7 and the 8. 7 is smaller. This index changes. We compare the 10 and the 8. It's smaller. This index changes. We compare the 10 and the 11. The 10 is smaller. This index changes, and we're out of room in the array, right? So in whatever control flow we're building to cover this, this seems like our stopping point, right? So we're only going to do this loop while the R1 index
Less than the arrow.
is in bounds. Let's say is in bounds. And R2 index is in bounds. We'll translate this in code here. Index is in bounds. So as long as these two things are true, we get to keep going. Once one of those isn't true, if we either go off the end of the world on the left side or go off the end of the world on the right side, then we have nothing more that we can be comparing. But are we done? Do we have everything in our array? So what's our last step, David? So we ran off the face of the cliff here, right? What are we missing right now from this array here? We're missing 11 and 12, right? If we run off the cliff on one side, the easiest way is to say, go ahead and take this array that you generated, and to it, add all of the elements between wherever this index is at the end of the array, and wherever this index is in the end of the array. Because those are things we haven't looked at yet. And if it so happens that there's nothing there, then we don't add anything. Then we look at the other array and we say, oh, there's two things we didn't look at. There's a gap. So those are the last two elements that we need to add to our array here.
So out of our condition, we're going to have like an else that handles that part, right?
After the while loop is done, we'll end our condition here by one of these going out of bounds, and then we're done with our loop. Our end state will only give us this amount of stuff here. And then we'll have to say, well, we ended our loop because we went off the bridge and we flew off and looked at all the things in one of the arrays. So then we have to find which array we did look at some stuff in, and take all those elements we didn't look at and put those into our array. Then we'll end up with our final sorted array. So this algorithm right here is called like a merge sorted arrays algorithm, or the merge part of merge sort. This exact question has come up like in at least 2 or 3 different interviews that I've personally talked to people about as like a question that they've just been asked. So it's a good algorithm to be familiar with in like the structure of like how we're putting those things together. Now, in terms of runtime, you'll notice this arrow looked at every element once and didn't go back, right? This here looked at every element and didn't go back. And because that's true, we only looked at every element once. So we know the runtime of this gives us that O of n that we were looking for a merge sort here. So let's figure out how to translate that into code now. We've done all the hard stuff, right? So we need 2 things here to track our arrays. We need our R1 index, which starts at 0, and we need our R2 index, which also starts at 0. We need our condition, which says while the R1 index is less than sorted R1.count, and the R2 index is less than the sorted R2's count, then we can do our looping structure. We're choosing, so this here kind of defines what it means to be in bounds, right? Because if R1 index is equal to sorted R1.count, then we're one past the end because arrays start at 0. Inside our structure now, we can start our comparisons. We can check and see if the value at sorted R1, at the index of R1 index, if this thing here is sorted relative to the R2 value, so that's sorted R2 at R2 index, then we know that we're in a spot where the thing on the left should come before the thing on the right. This is a little bit trickier conceptually than just a less than, but the is sorted closure, you can just replace that in your head with less than and it follows, right? So is sorted could just be sorted R1 and R1 index is less than sorted R2 and R2 index. Using this closure here just allows us to say it could be less than, it could be greater than, it could be talking about like a Game of Thrones episode number, whatever we want to be happening inside this closure. So now we're in the case where this thing here should be ordered to the left of this thing here. If that's true, then we want to take this thing here, append it to our list, and then increase our index number. Double the window? Try to get it open? Close it? Okay, so what are we doing here? So we're going ahead and then saying we want to do those two things. We'll need that array to be putting everything into. So some like a merged sorted R, perhaps. Also, I know I make this point every time I do it. Make sure not to call these like empty array. That's an easy thing to do when you're whiteboarding because you're saying, oh, I'm making an empty array. Always name things with the value that it represents, not what happens to be in it. So this thing represents the merged sorted array, and we're going to use that to capture all the values. If we called this empty array, it'd be confusing because we'd end up with a bunch of stuff in our empty array, and we wouldn't know what its purpose is. So we're going to take this merged sorted array, and we're going to go ahead and append whatever this value is right here. Then we're going to take our R1 index, and we're going to increment it. So that was our first case, right? That takes us through putting the 3 into this array right here. So now our pointer is pointing at this 6. We put the 3 in, and all this stuff hasn't been added yet. Now we're comparing our 6 to our 4, and we're saying, is it true that the 6 should be to the left of the 4? We're saying, no, we're trying to sort by less than, so that's not the case. We can then put the rest in our else condition. We could have another if statement that just checks to see the inverse, but we know this tells us if the thing at R1 should be at the left of it, and if it shouldn't be on the left, then it should be on the right. Or they're the same, in which case we don't care which one's on the left and which one's on the right, because it's the same value. We can then take our merged sorted array and add whatever the value is in the second sorted array at the current index that that pointer is pointing to. Then we can go ahead and increment that index. Once we've done that, our while loop will execute and will get us up all the way to comparing this 10 and this 11 here. And it will give us the 10 being appended, the index incrementing to 1 past the end. We'll come back to the top of our while condition. We'll say it is no longer true that R1 index is less than sorted R1.count. It's equal to it. So we break out of our while. Now we have to handle the last bit of how do we get the rest of the stuff in the array that we haven't looked at yet. We haven't looked at this 11 and 12. There are many ways we could do it. The easiest is to say, take the array slice for both array 1 and array 2 from wherever we ended up, the index, to the end of the array, and then just add that to the end of our sorted array. For the left side, that array slice contains no elements. So it did nothing, and that's fine. For the right side, it will contain only the things that we're missing. If it so happened that the left side had extra stuff in it, then we'd add the stuff from the left side, and the right side would have nothing. So doing that, we don't need to actually worry about which one had extra stuff left over in it. We can just say, just grab all of the stuff from the end, and if one of them doesn't have anything, then it doesn't get put into our array. So we take our merged sorted array, we add to it the array we get from slicing the sorted array 1 from whatever index we ended up with to the end. And to that, we then add the left side. Now, one of these is going to be empty, or our algorithm is broken. And that's okay. We don't actually need to know which one of these is empty. Our code here will tell us which one is empty by just building an empty array for one of those, and that will work fine. So it's sorted R2 from R2 index all the way to the end. And this should build our complete sorted array here. So let's take a look what happens when we feed it these values that we made here. So we've got test R1, which is equal to something, test R2 equal to something else. Let's go ahead and feed it with the same values we had up on our board, 3, 6, 7, 10. Test R2 will feed with 4, 5, 8, 11, 12. Then we'll go ahead and have our merged R is equal to merge, passing in test R1, test R2, and a closure that says, oh, these are sorted smallest to greatest, by the way. And then we can go ahead and print out our merged R and confirm that it, in fact, is merging those together as we would want it to. We don't have many elements in it. Or if we made a mistake in our condition. Okay, so this here is building our sorted array that has all the values we'd want to inside of it here. We can print out the merged sorted array here, which isn't going to tell us too much. It's just going to show us the this here being built one element at a time up until 10, and then the 11 and 12 will be added through this last step at the end. I guess the 10 is added here. So this is building it in pieces here and running through that algorithm. Yeah? So that's this is sorted right here. So what is sorted does is it takes in 2 arguments of the same type and tells us whether or not they're sorted. In our implementation here, or so when we're calling it, we pass it this as the way to compare elements. We're telling it how our arrays are sorted. We're saying they're sorted smallest to greatest. So inside here, when we're running it with this thing specifically, it's like instead of having this line here, we said if this value is less than this value. When we pass in this closure here, it's exactly the same when we're running it by replacing is sorted, these 2 things, with this expression here. Does that make sense? The advantage is, let's say that these were reversed. We could then tell it, oh, we're not sorting smallest to greatest, we're sorting greatest to smallest. And then this symbol here reverses, and we'll end up building a reversed collection Really? That's annoying. Good question. These are arrays of integers, so this $0 in this closure refers to the integers. I think this will work. We could make it conform to comparable. In our function, we only need that with this symbol here. Is sorted is just a closure. Could take in anything. Really? Let's do this long form. Let merged r is equal to merge test r1 test r2 by first num second num returns a bool in first num is greater than second num. Yeah. Can't tell me that's ambiguous. Really? Shocking. Oh, it's... Oh, does reverse not give me an array? Does it give me like a reverse collection or something? Yeah, that's nasty. So I think the type of these arrays is not actually integers, which is kind of annoying. Yeah, look at that. So the reason why that wasn't working wasn't because of anything about our closure, but when you call dot reversed, you don't actually get an array. You get back this reversed collection, which behaves like an array most of the time, but isn't exactly an array. So let's be less fancy and just flip these the old-fashioned way. 10, 7, 6, 3. And then here we've got 12, 11. We could just convert these to arrays as well. Being lazy. So if we have these as our test arrays, now we should be allowed to collapse our closure into by greater than, and see if that makes it happy. Gotta be very careful with some Swift errors, say, especially when you're running with like more complex lines. Sometimes the errors don't actually say what the problem is. So in this case, it told us ambiguous reference to member greater than, because it was trying to compare like a member of an array collection, like a reverse collection. It was just getting very confused. So here, we do the same thing in button reverse. And we can see that now our is sorted closure, instead of being less than, it's using greater than, and it's building our array correctly here. The point of using this closure is that the user can tell you how it's sorted, and then this swaps on the fly. Because otherwise, we'd have to have a merge by ascending order, and a separate merge by descending order function. And then if we had some other weirder ways we wanted to sort things, as well, all need different functions. So point of closures is to tell you more information about how to do something, right? How do I know if two things are sorted? And this answers that question. Okay, so this would work for smaller things. This would also work here if we had giant things in it. We can confirm that our sorts is working in a reasonable time just by putting big things in these arrays. So let's go ahead and take our, like, let's say we had 10,000 things, 1,000 things. Map and int.random in 0 to 10,000. So this here is going to just build a big array of random stuff. This is going to build another sorted array of random stuff. And we want to make sure that our merged array has both of those in order. I should not have this print statement. Thanks. It's going to take a long time. All right, anyhow, we can see as it's building, each of these steps here is preserving the sortedness of our array. We're constantly adding new sorted elements to the end of it. And if and when this eventually prints out all the garbage it has, it will in fact print out 1,000 things all perfectly in order. And importantly, we can see from the number of times it's operating here 5 times, pretty good. Looks like that tracker's not working. Anyhow, we run this print statement every time we're in our while loop here. We used to, right in here. And we should end up with roughly 1,000 print statements, even though we're having, we should have 1,000 print statements here that we end up with. We're about halfway through. Why should we have 1,000 print statements? I deleted the line here, but we had a print on this line right here. So this line should run 1,000 times. Usually it has this number telling us, but here it seems not to. That's okay. We can see that we're printing, every time we print, we basically add an element to it. So if we have 2,000 things, we're gonna need to print 2,000 times. So that's the right order of magnitude. If this was a quadratic algorithm, we'd have to print 1,000 times 1,000 times, which would be 1,000,000 times. That'd be a lot of times. This is a little more sensible in saying we're only gonna print on the order of magnitude, the same scale as what you gave me. So we had 1,000 statements, 1,000 things in our array, and we had print statements, and we still ended up finishing this in only a couple dozen seconds. So that's the right runtime for algorithm. Okay, so this is all the pre-work. Now we get to the fun stuff. So now that we have this algorithm that we feel good about, that we feel can actually sort these, I'll comment this out here. So now that we have our merge algorithm that can take 2 sorted arrays and merge them together, we're ready to figure out how we can build our merge sort that splits it so that it's ready for these pieces to be merged together. So how can we do that? So what we want to do is we get an array as input. We're building a recursive function. So we know we're going to need a base case and a recursive function. Our base case is going to say, if you give me one element, like r.count is 1, we can just return that array. That's our base case. If you give me an array with one thing in it, that array is sorted. I don't need to do anything. That's a sorted array. What we need to do next is take this initial array. If we have more than one thing in it, now we got to do some work. We want to split it into a right side and a left side. So we're going to make some left side, which is equal to something. We're going to make some right side, which is equal to some other array. Then, we want to say, apply this function we're writing now, merge sort. Apply it to the left side. Then apply it to the right side. And then, once those arrays are sorted, which they will be, merge them together. So we then call merge on our recursive function merge sort for the left side. Left. And merge sort on the right side. This line's super tricky. So what is this doing here? This is saying we're going to end up with a left side and a right side. We want to apply this recursive function to the left side. When we do that, we're eventually going to get down to a single element. That's what this function does. It just makes a left side and a right side. And if we have a single array, we return it. So this merge sort function that we're defining here is eventually going to give us a single element of just the leftmost side. It's also going to do that for the right side. It's going to split it all the way down until we end up with a single element on the right side. We'll split that off for any given array. So if we start here at the base level, if I give one element, I'll just return it, and it'll be sorted. If I give you 2 elements, it will make a left side and a right side, each of which is half, and then it will run that recursively on the left side of one element and the right side of one element. Those are both sorted, so those will return out to be those single elements here. Then, these collapse into that element that we return. We then call this merge sort here on this element. So once we call that, we have this array here, and we call merge passing those together. this will end up building this array. And if we started here, we go through here, we end up here, we're done. Right? So one way to think about recursive stuff is to take a picture and to start going back a step to see what happens. So if we start off with this picture, and we have how many things? 1, 2, 3, 4, 5, 6, 7, 8. Let's put 8 things in here, shall we? 3, 6, and 1, 4, 9, 7, 2, 3, 4, 5, 6, 7, 11. All right, so let's say that we have these values, just to give some names to things. 4, 9, 7, 11. 3, 6, and 1, 4, 9, 7, 11. And so if we started with this, if we start with this array 3, our function would return 3. And that's what our basic does, right? You give me an array with one thing in it, I'll give you back. Nice and easy. Going back a step, if you give 3 and 6 in, what happens? We take this here, we have more than one thing, so we keep going. We look at the left side then, we say we're going to make a separate array with only a 3 in it. We're going to make a separate array with only a 6 in it. Then, we're going to call merge, this, what we just wrote there. And the argument, the first argument is going to be what happens when you merge sort the left. The second argument is going to be what happens when you merge sort the right. For the left side here, when you merge sort the left, you end up with, we had a 3, we had a single value here, that gives us back 3. For 6, same thing happens. So this turns into merge an array of 3 and an array of 6. We can do that. That gives us an array with 3 and 6. For 10 and 1, we'll do the same thing. We'll split off into 10 and 1. Merge 10 and 1 will give us an array with 1 and 10. Then, let's say we started here, right? We've done each of these pieces out. Let's say that the initial array was 3, 6, 10, and 1. You give that array to the function. What it's going to do first is it's going to call merge sort on the left side of 3 and 6. We're going to merge sort of the left of 3 and 6. And merge sort of the right, which is 10 and 1. We can see from this here, we just went through this process with merge sort 3 and 6, right? We know that when we call merge sort 3 and 6, we get this array back. Right? We started here, we ended up here. That process made sense. So merge is going to then take 3 and 6 here, and merge sort of 10 and 1 is going to turn into 1 and 10. Then we need to merge 3 and 6 and 1 and 10. And that array is going to be built here, 1, 3, 6, 10, by the merge function that we just wrote there. So that collapses from here. We can do the same thing on the right side. This would build a 4, 7, 9, 11 array. And then if this is our input, we know how to merge sort this piece. We know how to merge sort this piece. So then we merge those two sorted things together to get back up to here. There are a lot of steps to recursive functions. It's incredible how much complexity is packed into like 5 lines of code. But it's also very clever that you can take this problem here, becomes part of a larger problem. And so that's the best way to think about recursive building blocks, is starting with the smaller problems and working up one layer at a time. So let's put some of that in code and put some print statements in to see what it actually does. So we're going to build our merge sort. And merge sort's going to take in the array we want to sort, which is some array of some generic t. And it needs to know how we're sorting it. Same closure that we had before. And this whole thing is going to return this here. We'll go ahead and name this merge sorted. Okay, we know our base case. If you give me an array that only has one value, we return that array back to you. So make sure that the array's count is greater than 1. Otherwise, we're just giving it right back to you. That's our base case. Now we need to get in the rest of our work. We need to make a left side, which is going to be equal to everything from the array start up to the midpoint. So that'll be here from 0 up to the midpoint, which is r.count over 2. Then we need to make our right side, which is the array everything from r.count over 2. We can make a variable to save that as well. To the end of the array. And because this is Swift, these are array slices. We want to make them real arrays so that we can use them just like we could any other array. So this is just building our left side and our right side. Now that we have our left side and our right side, we want to return, it's a bold thing to be writing this early into a function, what we get when we merge our sorted R1 as the merge sorted left side by is sorted. Our sorted R2, man, a lot of stuff here. Our sorted R2 is what we get when we have the array right side that's merge sorted. And then we're passing this is sorted closure, same as before. Again, an incredibly small amount of code here, but a lot of that work is hidden in the merge algorithm. So what is this doing? Notice what this process is here. We're taking a left side and a right side. We're then saying, go ahead and merge sort the left side. That's going to be the first sort. Merge sort the second side. That's going to be our second array. Then, once you've done and sorted those, just merge them. Nice and simple. So, let's take a look and see if we can see each of those pieces breaking down in the process here. Now, I might make this a little neater. I'll leave this here, but maybe we want to break out some of these arrays so that we can print them and get a little bit of understanding what it's doing. So I'm going to make this sorted left side is going to be this bit here. I'm just adding 2 more variables just to make it a little more clear for when we want to look at some print statements. Our sorted right side, it's going to be this bit here. Then we can go ahead and merge the sorted left side. Merged array is equal to sorted left side, and the sorted R2 is the sorted right side, and then passing along our is sorted so that it knows how to be sorting them. Then we can return the merged array. It's the same code as we had before, just being a little bit more explicit about our variables as we're naming them. So that we can get this nice print statement in and see what this is doing as we're writing it. Okay. So let's go ahead and take this same array that we worked with before, put it into merge sorted, and let's see each of those merged pieces that it's coming up with as part of the process here. And also we'll have and tell us what the array is that it's looking at. Running merge sort on R. And the merged array is always good to have your functions talk to you, give you a little better understanding of what they're working with. So let's go ahead and take this new test array here. That's going to be 3, 6, 10, 1, 4, 7, 11. Missing something? Am I missing? 3, 6, 10, 4, 7, 9. Thank you. Okay. So now we can go ahead and run our merge sort on test array by less than. And when we run this, our print log will tell us each of those different pieces it's sorting in our process. And we can use that to see if it's doing it any differently than how we drew our picture. Always a good start. Playground says it's good days and it's bad days. I can try. Kind of frozen right now. Yeah, I think I have to force quit Xcode. Farewell Xcode. I'm probably saved. Okay. We only had 10 things. Shouldn't break that much. Okay. You didn't sort the one? Really? That'd be fun. I'd be up for some debugging. That's good. All right, so now we'll call it on this here. There's a request to scroll up. This is what we got in our merge sort right now. I'm just going to put some REPL. All right. While Xcode is crapping out, I'm going to take this and put in a REPL. Languages Swift. Okay. Because if this was giving us an infinite loop, it would at least be printing out something every time, so Xcode has been a little bit slow there. It's a very deceptive loading bar here. All right. Okay, so just putting this in a REPL here. So here, it's now printing out each of the different things that it's sorting in the process. First thing that it does is it says, I'm trying to run merge sort on this whole thing. Well, that's good, because that's what we told it to do. Then it says it's running merge sort on the left side. Then it's running merge sort on the left side of the left side. Then we don't need to run merge sort anymore, because we only have one on the left. Although we could make that print statement a little more explicit if we wanted to. You might as well make that a little bit more clear. So I just flip that to have it talk to us at the top line here. It's going to be really small. Okay. So here it's telling us what it's running. And it says, I'm looking at the whole array. That's what he gave me. Then it says, I'm going to be running it on just the left side. Now I'm running merge sort on just the left side of the left side. Now I'm running merge sort on just the left side here. Now it just returns the array. We know this just returns the same array. So that's done. It's finished running from this 3-6 track here. It says, I need to run merge sort on the left side. Then, once that's done, I need to run merge sort on the right side. Running merge sort on the left side gives it 3. It's done. Now it runs merge sort on the right side, on the 6. Then, we merge together the 3 and the 6, and it tells us that the merged array is 3 and 6. This side is now done. It's run merge sort on the left side. Now it runs merge sort on the right side. We look at 10 and 1. It then runs merge sort on 10, which just returns 10, 1, which returns 1. Then it merges those two together and gives us 1 and 10. Great. We've run merge sort on the left side. We've run merge sort on the right side. So now we merge those together, and it gives us the merged array 1, 3, 6, 10. Great. We've run merge sort on the left side. Now we run merge sort on the right side. To run merge sort on the right side, we first need to run merge sort on the left side of the right side. Then we need to run merge sort on the left side of the left side of the right side, and end up with this 4. Then we run it on the right side of this bit, of this 9, 7 rather, and then we end up with 4 and 7 as part of our block there. I think I swapped the order there. Then we do the same thing for the right bit, that 9, 11, or 7, 11, swapped in this. Then once we do the left side and the right side, we end up with this bit all sorted here. We've run merge sort on the left side, we finished that. We've run merge sort on the right side, we finished that. So now we merge them together. And it merges them together into our final merged array. Now, if we had a much, much bigger input, it would do this just for many more things in our array, right? Like, let's imagine, let's have it work with a little bit of a bigger array and see what it does with it. Let's take maybe just 20 elements. It's still going to take a lot of operations, but we're going to have it run with 0 to 20 dot map dot underscore in dot random in, I want to say. Let's try that. So here, and you can notice it runs very quickly. Now it had these random elements to run on. So it's going to do the same thing that it did before, which is it's going to take the left side, everything up to this bit right here, and it's going to run merge sort on that. Then it's going to take the left side of this left side and run merge sort on that. Take the left side of this bit, run it on that, end up with a single element and a single element, merge those together. It'll back up a step again and handle these bits. It'll split those up. Might be uneven, might get 1 and then 2, so I might have to do it again. End up with single arrays and end up with this bit sorted here. Then once this piece is sorted and this piece is sorted back from this thing, it merges them all together and gives us this bit here. So you can see that it breaks it down into these single building block arrays. Then, once it's broken it down into these individual elements, it merges back together. And once we're at the rebuilding step, we just need to wait for these pieces to break down, get built back up, and become big enough for us to know what we're supposed to be merging. Right? We run merge sort on the left and on the right. In order for us to get to this side, we need to know what this side looks like. Thus, in order for us to get to this side, we need to know what this side looks like. In order for us to get to this side, we need to know what this side looks like. So we do this side. Now we know what this side looks like. So we do this side. Now we know what this side looks like after we merge them. So we do this side. Then we know what this looks like. Now we can do this. Yeah.
I see like the line
Yep. Yep. So like, what happens if we have a bunch of duplicates in our array, right? How is that handled? In our implementation, there are several different ways you could handle it. I just woke up. Mm-hmm. So let's say you're saying like, well, what happens if there is another 3 here? And there's another 1, and there's another 4, and there's another 7, and another 9. Like, how's it handling all of these duplicates, right? Look at the is sorted closure right now, right? Is it true that, let's say, 7 is less than 7? No, right? So what do we do? If this if statement's not true, then what do we execute? The else block. So we'll just happen to run this code, right? So what this is telling us is the way that we built it, again, there's many ways you can build it, but if we have something like this here, and we're trying to merge these together, right? This will say, is it true that the thing on the left should be, that this element should be to the left of this element? We say no. It's like, well, fine, I'll put this element on the left. Now we compare these. Should this thing be to the left of this thing? Yeah. And then we end up back in the state, that's fine. So we're handling it implicitly. It's a good catch. It's always great to be thinking about edge cases like, what happens if values are not unique? How are we handling that? That's a very common edge case you'll get. In our case, we're handling it by saying, we actually don't care which of the equal values we put in first. They're the same, right? As long as, now, maybe you have some like other way of where you say, well, even if their values are the same, I want you to do something else because there's some other property that's important. Then they specify that in the closure. And they say, well, the closure might say if two people have the same name, then you should be sorting instead by their age or something, whatever. The sort closure will then dictate that, and that will get captured by the experiment. Okay. That's a good question. Okay, so that is the gist of what our merge sort algorithm does. There's also a picture here at the bottom that talks about this process, and you can see this includes the numbering of what step everything is being accomplished in. We start off at the top, number 1, is to sort that stuff. The second thing we'll do is run merge sort on the left side. We're going to have to wait to run merge sort on the right side until we've sorted the left side. So we do the left side there, and you can see that the numbers are hugging the left side really tightly. Because the way this works is sort the left side, then deal with the right side, then merge them together. So the last thing that we'll do is, well, end up sorting this bit down here before merging them together. So we'll end up sorting the whole left side of it before we even touch any of the elements on the right side. And you'll see this as well. This is a little preview for when we get to talk about free traversal algorithms. This would be a standard free order traversal here, where we'd be visiting stuff in order from left to right and printing something just as we find it. Okay. Other questions on merge sort? So big takeaways. It's a recursive algorithm. It's a divide and conquer algorithm. Merge sort works in 2 pieces. It breaks an array into individual pieces. Then it has a special algorithm called merge, which takes 2 sorted arrays and gives you a single sorted array in linear time. Once you have an array of size 1 and another array of size 1, it's very easy to put those together into a single sorted array. So you're guaranteed your first step, and then your algorithm can tell you how to do that index pointery stuff to end up merging those together. The merge sort is a linearistic combination of a recursive algorithm that chops everything up into single bits, and a merge function that lets you go from 2 sorted arrays into 1 sorted array in linear. Yeah. Like inside Swift? Well, there's the, I mean, I can kind of cheat. If you type in merge sort, it's in Swift. So someone built it. I don't actually know what this is used for. Like, I know that, yeah, to like, again, these types are so bizarre, I can't imagine this is like an end user facing API here, right? Like, there's no reason why you would ever want to be calling something that had a type of unsafe mutable raw pointer. It sounds like a really bad idea. This is for like really low level memory access stuff that probably the API developers want to do when they're building other things. I can tell you, because I know quicksort is, I believe, what Swift uses in their sorting implementation. I don't know if like this particular merge sort is used for anything in Swift off the top of my head. It might be, but I'm not actually sure if the API designers did anything with that. I don't think there's a built-in merge, is there? There's a merge sort. I think the merge sorted array is something that we had to write. I don't think that comes up enough for them to like give you an API for. Yeah, that's ours. So, like many things, this is some people probably use this when making something fancy. Like maybe some of the weird reverse collection sorts happen to use like this for some reason. Maybe it's better. I don't know. But if you should never have to be like writing APIs that talk about this, like unless you're doing very low stuff. So there are other programming languages, I think, where just like Swift uses quicksort, like Kotlin, for example, might use merge sort. Like, I'm not sure off the top of my head, but totally possible. And the reason why you want to use one and not the other is if you don't feel good about picking your pivot. Quicksort degenerates into quadratic, I don't even know what they call that, quadratic arithmetic, maybe that's a real word, n squared log n, if you pick a bad pivot, you just end up only getting rid of one thing at a time. Merge sort, you'll notice, we didn't have to do any work to figure out how to split in half, we just cut it in half. The downside is we had to break it down and then build it up again. Quicksort didn't have to do that. It just broke it down, and once it was broken down, all of the pieces were in order and just smashed them all together. Merge sort's got to break down and then build back up. But importantly, even though we have really another level of depth here, which is log of n, as you're calculating the runtime, you might say, well, hang on, we really have two, or O of 2 log and log n here. You might say, hey, hang on a second, shouldn't this be the runtime? We can break it down, we have to build it back up. In big O notation, this 2 doesn't matter at all when you're talking about like 10 million elements. So you ignore any of the constants that appear before them, any of the coefficients. Because as you're sorting a million elements, 10 million elements, this 2 doesn't make a bit of difference. We only care about values which scale relative to how much stuff we have. Log of n is very slow to grow, but it does grow relative to our input. 2, doubling something, does not grow relative to input, just doubling. It's not special based on like how much more stuff we have. Okay, other questions on merge sort? Neat, we did. That's the last sorting algorithm that I think you need to know. There's some fun ones, but that was good, right? There's you can look up, there's some fun ones. There's radix sort. Radix sort is a constant time sort that only works for numbers. It's very, very weird. I think you've seen the most important ones though in insertion sort, bubble sort, quick sort, and merge sort. If you're familiar with the pictures and can explain those, and you can do the merge bit of merge sort, you're probably good to go for sorting algorithms. If you have a little more time, be familiar with like coding up some of the recursive algorithms. But the big takeaway is if you can just explain in words how each of these things works, you're going to be in a better place off than like a lot of people who actually have like CS degrees and spent time doing this, because a lot of them have no idea what they're talking about. So try to just remember the picture for each of these and be able to explain how it's broken up and put back together for merge sort. It's a big idea. Big idea for quick sort is dividing in half that pivot. Bubble sort is taking big elements and bubbling them up to the end to where they belong. And insertion sort is keeping a sorted section at the beginning, iterating over the array, and then as you find new elements, incorporating them into the sorted section at the beginning. Okay, so for merge sort practice, for this one here, there's just a link because there's some better resources on this. There's a few links to some external resources. If any of them are just telling you sort an array and they're just providing test suites for them, you can use merge sort to make sure that you understand it. You can also use that test suite as an opportunity to be seeing if you can remember how to code up bubble sort, or remember how to code up quick sort or insertion sort. Then there's also a couple here which are more practice with linked lists. Another interview question someone's gotten before, which is write this algorithm, but write it for linked lists instead of arrays. So got these up here and some practice with this stuff. You also have passion projects, you got labs, you got lots of stuff. So let me not take up too much more of your time. Be here if you have any questions, and thank you all for learning some sorting. I will Slack out the repo. Thank you for your reminder. Yes. Let me just Slack this out.
Yeah.
What's that? I should probably stop there, right? Oh, it stops recording when I unplug it. That's why I usually remember. I don't think it's intended.